Welcome to our third lab. It circles around gravitation, black hole mass, and multi-body orbitals. We will be exploring gravitational interactions through computational physics, estimating black hole mass from stellar orbits, and simulating complex three-body orbital dynamics. The purpose of this lab is to estimate the mass of a black hole, given a star with a given mass orbiting around that black hole, and to simulate the motion of a spaceship in a figure-8 orbit around a planet and its moon by calculating the gravitational forces acting on both the spaceship and the moon and using Newton's second law to predict their motion. The model for this experiment is coded in VPython and simulates the gravitational interactions between a planet, its moon, and a spaceship, and it calculates the gravitational forces between the bodies, updates their positions using Newton's second law, and visualizes the moon's circular orbit and the spaceship's trajectory in a figure-8 path based on the initial velocity input, ensuring the spaceship doesn't crash into either the planet or the moon. The main results showed that the black hole mass was about 1.2 times 10 to the 34 kilograms, and it was nearly impossible to make the spaceship move in a desired figure-8 orbit. The main physics concepts used are Newton's second law and gravitational force. Newton's second law, where force equals the mass times the acceleration, helps calculate the acceleration of the spaceship and the moon based on the net forces acting on them. And gravitational force, given by the force equals to the gravitational constant times both of the body's masses divided by the distance between the masses squared, which is used to determine the attraction between the bodies, allowing us to predict their motion. And by ensuring the acceleration, we can find the mass of the black hole through the relationship between force, mass, and acceleration. For the first part, we have the following initial conditions. We have that our system is the star, our surroundings is a black hole. The star has a mass of 2 times 10 to the 30 kilograms. The time interval between data points is 24 hours. We start with the time of 0, and the initial position and velocity of the star are randomly generated but not specified in the conditions. And for our second part, our system is a spaceship, and our surroundings is the planet plus the moon. The planet is at the origin with a mass of 8 times 10 to the 27 kilograms and a radius of 4 times 10 to the 7 meters. The moon is positioned 9 times 10 to the 8 meters from the planet with a mass of 6 times 10 to the 25 kilograms and a radius of 2 times 10 to the 7 meters. The spaceship is positioned at the surface of the moon facing the direction of its motion, and the gravitational constant is the gravitational constant. In part 1, the change in velocity and momentum of the star is calculated using initial and final velocity components, and from this, the change in velocity and momentum are computed, and the rate of momentum change is used to find the net force on the star using Newton's second law. The force is then broken into parallel and perpendicular components, and the black hole mass is estimated using gravitational force and distance. And in part 2, the gravitational forces on both the spaceship and the moon are calculated, and then the net forces are used to update their positions and velocities using Newton's second law. And the simulation includes break conditions to stop if the spaceship collides with the moon or the planet, and the positions are tracked over time and their trajectories are visualized. For our results in part 1, the black hole mass was estimated at 1.2 times 10 to the 34 kilograms using Newton's second law and gravitational forces on the star. In part 2, achieving a figure-8 trajectory proved nearly impossible due to extreme sensitivity to initial velocity conditions, and the greatest time without collisions was 350,983 hours using the initial velocity from the conditions. Despite efforts to stabilize the orbit, the spaceship often collided with the planet or moon, highlighting the sensitivity to initial conditions. For our discussion, some possible sources of errors include the small changes in starting velocity or position can drastically change the outcome. The three-body systems are chaotic by nature and unstable. We also have some gravitational assumptions. Point mass assumption ignores shape and mass distribution for each of the bodies, and it also neglects factors like radiation pressure, relativistic effects. Now, to answer the what-if questions, what does it mean? Well, the rate of change of momentum shows how the star's momentum is changing over time due to forces acting on it, while the net force is the total force responsible for this change. The parallel and perpendicular components break the force into directions relative to the star's motion, helping us understand how the force affects its speed and direction separately. And for the second what-if question, to predict the system's motion, the model must account for gravitational interactions between the black hole, star, planet, moon, and spaceship. Dominant interactions depend on mass and distance, with the black hole's gravity dominating near the star, and the planet-moon force is strong near the moon. All forces must be considered, as even weaker interactions can significantly influence the system's behavior over time. In conclusion, the experiments proved insights into gravitational interactions and orbital mechanics. We were able to estimate the mass of the black hole, and we explored the motion of a spaceship, moon, and planet, discovering that achieving a stable figure-8 orbit was highly sensitive to initial conditions and almost impossible to maintain. And that's all. Thank you.